Hello everyone, my name is Aidmar Wainakh. I'm from the Technical University of Darmstadt, Germany, and today I will present you the user level label leakage from gradients in federated learning, which is a collaboration work between Privacy and Trust for Mobile Users Research Training Group and Telecooperation Lab, and also the Artificial Intelligence and Machine Learning Lab. So let's start from the end of my title. So what is federated learning? So federated learning is a machine learning technique was proposed by McMahon in 2016 to train a collaborative model actually under the coordination of a central server. And the process starts with the server sends an initial model to the users who will train the model locally on their own data and send back the gradients of this model to the server. The server aggregates all these gradients and obtains the updated global model and send it back again to the users. And we go through multiple iterations till we get the model converged. And actually, the main privacy advantage of this technique is that the data of the users never leave their own devices. So it's not shared. The users do not share their data with the server, but they are only sharing their model gradients or updates. And if we are talking about a neural networks model, so here we are, the gradients actually are the derivative of the loss function with regard to the weights which are located on every edge in our neural network. Now the question was how risky it is to share the gradients with the server. So if adversary acquired or got these gradients, so how much information they can learn about our labels or our training data. And in this work, actually, we are focusing on the labels. And by the labels, actually, we are referring to the piece of information which describe our training data. So if we are talking about classification task here, for example, so the image would be our data, and the cat or the label cat is the label. However, the labels can be actually quite sensitive. So in medical application, for example, so the data can be the medical record of some patient, and the label might be might refer to the diseases of this patient. So there are some works already in the related work where they are actually investigating the leakage of the labels from the gradients. However, in these works, actually, they are focusing only on the case where the batch size or the batch are of small sizes. And in our collaboration or in our contribution, we went after arbitrary batch sizes. So we want to investigate this leakage when we have different batch sizes. And we were able to identify two gradient properties that expose the labels. And we exploited these properties to perform our attack. So what are these properties? So the properties actually are found or were found in the gradients of the last layer of a neural network. So what right before the output layer. And the first property says that if the gradient is negative, that means the corresponding label exists in the batch. So if the gradient of the cat here is negative, that means, sorry, definitely there is a cat image in the batch or in the training batch. And we proved this property mathematically, and it's actually generalization of another finding from our related work. And the question remains here is how many cats are there? And to figure this out, we derived the mathematical expression of the gradient, and we showed that it indeed relates to the number of occurrences of the label, which is lambda cat here, and also relate to the batch size, to the prediction scores, and to the output of the activation function in the previous layer. And the last actually two components are not accessible by any adversary because they are intermediate output of the calculations happened on the user device. while training the model. However, we noticed in our empirical analysis that the sum of the prediction scores is close to zero when the model is untrained, and that we can express the gradient value as a linear equation of the lambda, where we define m as the impact, which is the change of the gradient value caused by one occurrence of the label. Based on this observation, we formulated our second property, that is, in untrained model, the gradients are approximately proportional to the number of occurrences. Additionally, we noticed that the gradient is shifted sometimes with a positive value. We call it offset. We explain this shift as a result of misclassification penalty. So if we pass a dog image to the model in the training phase, and the model misclassifies this image as a cat, the gradient of the cat will receive this shift or this penalty. Now, we know that if we know the impact and the offset, we can derive then lambda. So we propose heuristic methods to estimate the impact and the offset. And there are three scenarios. I will present two of them today. First scenario, where the adversary has access to the shared gradients. And here we estimate the impact as an average of the negative gradients, because we know that these gradients correspond to existing labels in the batch. And we found also empirically that multiplying with the factor of 1 plus 1 over n improves the estimation of the impact, where n is the total number of classes. And in the second scenario, the adversary has access to the gradients and the dataset with the same classes as the original one. Here we can estimate the offset also of the cat by producing misclassification cases. We do that by passing patches full of labels other than the cats. We do that for several times and take the average of the cat gradient. Now, based on these parameters, we proposed an algorithm to extract the labels, and I invite you to have a look at the paper in order to see details of the algorithm. Now, we evaluated our attack by conducting an extensive set of experiments, and I will highlight part of them. We used the success rate as a metric to measure the effectiveness of our attack, and we looked into different batch sizes, data sets, federated learning algorithms, and model architectures. Today, I will show the results of a basic CNN model, and also we studied the attack under different convergence status and defense mechanisms. And we compared with the random guess and the deep leakage from attack as baselines. So again, we test our attack under two scenarios. The first, where we are estimating the impact, and the second, where we are estimating both impact and offset. And looking at the different batch sizes and data sets, we can see for MNIST data set, our attack under the auxiliary knowledge actually outperforms the DLG. And we see that all the attacks actually are effective and having rates way higher than the random guess. On the CFAR dataset, where we have 100 classes and more complex images, our attack performs quite good under both scenarios. And finally, for CELIP-A dataset, where the images are of higher dimensions, we see that the DLG degrades significantly, while our attacks still perform more than 95% for the auxiliary knowledge scenario. It's known that when the model is more trained, the gradients are less informative. So we studied our attack under different model convergence status. And we can see in this experiment that increasing the model accuracy, which is in black here, actually led to a decrease in our attack success rate. However, even with the model accuracy of 90%, our attack success rate are still more than 60%, and performing better than the random guess, which indicates that the information leakage still exists. Finally, to mitigate our attack, we investigated three defenses on the user side. So first, we added Gaussian noise to the gradient before sharing them with the server, and we tried different standard deviation. As we can see, the attack success rate decreased, but it's still effective, better than the random. With differential privacy, we clipped the gradients and then we added noise. We tried different clipping norm bounds beta, and for beta 1, we can see that the attack is not effective, especially for batch sizes more than 16. However, this defense also led to a remarkable drop in the model accuracy from 93 to 52. Finally, we tried gradient compression technique where the small gradients are pruned to zeros with different theta ratios. We see that the theta 80% can mitigate our attack while maintaining high accuracy of 92. We conclude that this defense is effective against our attack. By that, I would like to conclude my talk where we showed that the gradient sign and magnitude can indicate the ground truth labels, and we propose an attack to exploit these properties and extract these labels. And our evaluation showed that our attack is effective under different patch sizes and number of classes and model architectures and also training stages. And our also evaluation suggests that gradient compression is an effective defense. By that, I would like to end my talk and thank you very much for your attention.